One reason for the failure of a fluid to move according to the flow net is the phenomenon known as separation, which occurs in boundary regions of too rapid deceleration. As we shall see in a subsequent film, such separation is often the result of appreciable rotationality due to viscous shear along even a smoothly curved boundary. A type of separation which is of interest now is that due to boundary angularity. The flow net for a sharp boundary angle would call for an infinite velocity at the corner, which is physically impossible. Instead, the flow separates from the boundary, and the mean surface of separation tends to assume a curvature which is compatible with the requirement of constant pressure along it. The formation of secondary eddies in the separation zone is eliminated in the case of a liquid jet in contact with the atmosphere. The shape of such a jet beyond the point of separation from the boundary can now be predicted from an analysis related to the flow net, and orifices and nozzles thus become useful flow meters once the degree of jet contraction, and thence the Euler number, has been determined. In our previous films, separation of flow from a boundary was treated as a purely geometric effect. A plate or orifice diaphragm, for example, is usually too thin for the flow to follow without an impossibly low pressure at the edge. Separation simply reduces the curvature of the limiting streamline till a physically possible pressure field is realized. In general, however, separation requires not only an adverse pressure gradient, as in any region of deceleration, but also a zone of already retarded flow, as is produced by shear in the boundary layer. Here, the central streamlines do not separate as the pressure rises toward the point of stagnation, because the flow between them is not otherwise retarded. But the fluid in contact with the splitter plate is already at rest and cannot be further decelerated, so that separation must take place if the flow is to continue. As the boundary layer develops around any body of appreciable curvature, the point of separation rapidly moves forward from the zone of maximum pressure rise at the rear to the zone where deceleration first occurs. As a matter of fact, no change in boundary alignment is really necessary, just so long as there is a shear zone of low velocity and an adverse pressure gradient, such as prevails beneath the front of this undulous surge, moving slowly against the flow. Separation leads to three important occurrences. First, it changes the anticipated flow pattern. For instance, this channel expansion obviously does not cause the flow itself to expand as rapidly as desired. Secondly, it produces boundary drag, thereby expending energy through the generation of eddies, which rapidly transform to turbulence. Finally, it can lead to oscillation of the flow, with a corresponding pressure fluctuation, boundary vibration, noise generation, and perhaps even structural damage. Though separation is very essential in the operation of parachutes and baffles, it should in general be avoided by the control of the boundary layer or the pressure gradient, or of both together. If the boundary moves with the flow, for example, the retardation by shear is offset, and separation obviously is prevented. Much the same elimination of separation is realized if, as is now beginning to occur, fluid is discharged tangentially into the boundary layer region through boundary slots. Even better results will next be seen to obtain as the boundary layer fluid is sucked into the slots as rapidly as it is retarded. A change in the pressure field as a whole is provided by the introduction of guide vanes. These can be made to conform to the original boundary and thus increase the relative radius of curvature locally, or else the whole structure can be redesigned accordingly, as in the case of this miter bend. The flow is obviously much worse without the vanes, but much more efficient once vanes have been installed.